Good morning, it's Mrs. Marquette. Today we're going to talk about graphing a new type of function. So we're starting chapter 8. The first two lessons are going to be all about graphing, specifically about the exponential growth function today. Before we start talking specifically about this type of function, I want to review just a couple things. First of all being domain, and then the second one being range of any function. So if we recall from way back first semester, chapter 2, the domain of a function, those are all of the x values or all of the possible x values. And the range is all possible y values. So when we talked about domain and range, we would talk about what x values did I plug in, what y values did I get out for the range. But we can also look at the graph of a function and decide what their domain and range values are. So if I look at this first one, this is like a calculator window. So I can assume that this graph continues on forever. So this is the graph of y equals x squared, or a parabola. Now, if I think about all of the possible x values, I can do this kind of in one or two ways. I can look at the graph and say, for every single x value, like the x value 2, or if I did the x value 3, I could see that this would keep going, and if I did the x value 4, 5, eventually my graph is going to intersect each of those x values. Okay, if I would extend it, I could find a y value for each of my x values. So that's in the positive direction. Also in the negative direction, if I look, -1 does have a y value on the graph. -2 does hit the graph as well. -3 is an x value. Eventually my graph would intersect as well. If I went out further, -10, -100, -1000, all of those x values would eventually have a y value as well. I can also see that if I looked at the actual formula for the function, y equals x squared, think about plugging in really big x values, you would get y values. Plugging in really negative x values would also get you y values. And then also notice that the x value 0 is also on our graph. So what that really tells us is that every single x value can be a domain value in this function. So I'm going to say that my domain is all real numbers. Okay, because every single x value on my graph can be plugged in. It has a y value on our parabola y equals x squared. Then I look at the range values. These are our y values. So I go the other way. I look at like the y value 1, the y value 2, 3, 4, 5. All of those positive y values do have an x value. So I could assume that this was going on forever. And even if I plugged in really large y values, like 100 or 1,000, I could extend and hit my graph. This is also true for the y value 0. That is on the graph. But if I take a look at the y value -1 or -2, -3, -4, and so on, none of those y values will intersect the graph. None of those have an x value. So it looks like our range is actually restricted a little bit. So our y values have to be in a particular form. Specifically, they have to be the positive ones. So I say that y is greater than 0. But I could also have y being 0. So I say y is greater than or equal to 0. Then we'll look at y is equal to the square root of x. I'm going to go and look at the domain first. So it looks like all of my positive x values do indeed have a y value. This continues. So even way out here, I could intersect my graph. But then if I look at my negative x values, none of those actually have y values. If I look at this equation, plugging in negative x values, that will give me an I. Okay, remember that negative under a square root is an imaginary number. So my domain here is going to be x has to be greater than or equal to 0, because technically 0 is on the graph, and I can take the square root of 0. The range is very similar. I can hit all of the positive y values. That will eventually intersect. But all of these negative y values never get hit by the graph. So my y's also have to be greater than or equal to 0. So we'll see how this plays into our graphs today. Pretty much we're going to be graphing functions and then deciding their domain and their range. So an exponential function involves the expression b to the x, where the base b is a positive number other than 1. So I'm looking at this b being called the base because it is the bottom of our exponential. Here, our exponential means that our variable is in the exponent. So let's actually take a look and see what happens when we graph this. When I plug in, let's actually plug in the positive numbers first because that's usually a little easier. If I plug in the number 1 into this equation, f of x equals 2 to the x, I get 2 to the first. 2 to the first is 2, so the 0.12 is on my graph. If I plug in 2 into the exponent, I get 2 squared, which is 4, so 2 4s on my graph. And then if I plug in 3, I get 2 to the third, which is 8. So 3 8 is on my graph. Then I can do 0. If I plug in 0, this is the weird one. Remember that anything to the 0 power is 1. So I get 1. I can plug in negative numbers as well. So 2 to the negative 1 is a half, or 0.5. Remember that taking a power to the negative or a negative power will flip so that you have a fraction. So then negative 2 will be 1/4 or 0.25. I will take either. And then negative 3 is 1/8 or 0.125. So go ahead and graph all of those points on your graph. So there are just the points. I can see that as I go off to the right, my y values are getting bigger and bigger and bigger, and it looks like that'll continue. But if you take a look at these values on the left side, it looks like they're doing something kind of interesting. They are decreasing as I go right to left, but they look to be getting closer and closer and closer and closer to 0. In fact, those y values are never going to hit the x-axis, that 0. If I think about it, it's because if I plug in even very large numbers like negative 100, I'd be taking 2 to the negative 100, which is 1 over 2 to the 100. 1 divided by anything is never going to be 0, so I'll have just a really small number. This is so special, in fact, that we are going to draw a little line right here at the x-axis. That is kind of like, you can think about it kind of like a force field. Like it's a number or it's a line that our graph is going to approach, but it's never actually going to hit. We call this an asymptote. So I'm going to write that word down for you. So our horizontal asymptote, again, it's a line, this time it's y equals 0, that our graph approaches, but it can never hit and it can never cross either. So it's kind of like a force field that keeps our graph all above or all below our asymptote. So we can actually talk about our domain and range here as well. So I've got domain and range and horizontal asymptote. I'm going to call it HA. Okay, so horizontal asymptote is y equals 0. Our domain, we can look at those x values. It looks like our x values are both going in the positive and negative direction. You can see that the arrows go both right and left. So our domain is all real numbers. But our range, remember that I can't cross that asymptote, and I also can't hit it. So it looks like all of our y values are above that asymptote. So y is actually bigger than 0. It can't be equal to because it doesn't hit the asymptote. This is the kind of shape we're going to be seeing all day, where we've got one side approaching the asymptote and one side going away from the asymptote. So let's actually talk a little bit about the characteristics of this graph. If you plugged in these two graphs onto Desmos or a graphing calculator, here's kind of what you would get. I get y times 1/3 2 to the x. I would have a graph that looked kind of like this. And the point 0, 1/3 would be the place that it intersected the y-axis. Whereas y is 3 times 2 to the x, it would have the same general shape, but the point where I cross the y-axis would be 0, 3. This is important because I've got this number being the y-intercept in both cases. Additionally, if I had y is negative 1/5 times 2 to the x, I would have this shape. The point where I cross the y-axis is negative 1/5. And for y is negative 5 times negative 2 to the x, I have this shape, and you guessed it, I have 0, negative 5 as my y-intercept. Notice that when my number out front is positive, I have my graphs above the x-axis. When my numbers are negative out front, I've got my graphs below the x-axis. This is always going to happen. There's a few other things that we can notice about every single exponential growth function. So if I've got y equals a times 2 to the x, this number a is always going to be the y-intercept. So the point 0, a, is always going to be on our graph. We can notice that that is because I've got y is a times 2 to the 0. 2 to the 0 is always 1, so that's going to be a times 1, which is a. Okay. The x-axis is an asymptote, or a horizontal asymptote of the graph. That's that line y equals 0. The domain is all real numbers. This is the sign for real. It's like an R with a double bar. The range is going to be y is greater than 0 if a is positive, and y is less than 0 if a is negative, meaning that my entire graph has to be either above or below that asymptote, because we kind of think about it like a force field. You can't pass through that asymptote. If a is positive, we've got y is greater than 0. If a is negative, y is less than 0. So when we graph an exponential growth function, we can actually do so by making a chart and kind of remembering what the shape of our graph should look like. So if I have y as 1/2 times 3 to the x, I'm going to take an xy chart, and I'm going to plug in 3 very simple numbers, 0, 1, and 2. Okay, so when I plug in 0, I get 1/2 times 3 to the 0. Which is actually just 1/2 if you plug that into your calculator, because 3 to the 0 is 1. So I know that the point 0, 1/2 is on my graph. 1 is 1/2 times 3 to the 1, which is 1.5, or 3/2. And then when I plug in 2, I get 1/2 times 3 squared, which is 4.5. I can graph all of these points on my graph. I've got 0, 1/2, 1, 1.5, and 2, 4.5. Okay, so my y-intercept I know already is 0, 0.5. I could have been able to tell that from the number out front, or because when I plugged in 0, I got 1/2. For your y-intercept, you're always going to have whatever number you get when you plug in 0 for x. Our asymptote is always going to start at y equals 0, or our x-axis. So I can draw that. And now when I actually connect my dots, or connect my points to make my graph, I can kind of remember the shape of the graph. I know that one side has to approach the asymptote, and the other side has to go away from the asymptote. So I'm going to say connect the dots and keep going. So it looks like the side that's close to the asymptote is the left side, so I can make that approach the asymptote. And then I will connect the dots and keep going on the other side. And that's the graph. My domain is going to be all real numbers. It's always going to be all real numbers. And my range is going to be all of the y values above or below the asymptote. So the asymptote is 0, so y is going to be related to 0. And this time, all of my y values are above the asymptote. So I say y is greater than 0. That's kind of going to be your process every single graph. Graph your table, find your asymptote, remember the shape of the graph, and then finish your graph. Number 2 is y is negative 3/2 to the x. If it helps you, you can put a -1 out front. So I can have my chart x and y, and I'm going to plug in 0, 1, and 2. When I plug in 0, I get -1 times 3/2 to the 0. Remember that anything to the 0 power is 1, so I get -1 times 1, or 1. Then -1 times 3/2 to the 1 is a -3/2, or -1.5. And then the last one, when I plug in 2, I get -1 times 3/2 to the 2 is -2.25. Remember, when you plug this into your calculator for this last one, I would literally plug in -1 times 3 divided by 2 caret 2. And when you do that, you should get -2.25. So let's try graphing this. I've got 0, -1 is on my graph. 1, -1.5 is on my graph, and then 2, -2.25 is on my graph. What I know is that my horizontal asymptote always has to be at y equals 0, so we can draw that. I draw it with a dotted line because it's not really on my graph, it's just kind of like a force field. So I can look at which side approaches the asymptote, which side connects the dots and keeps going. So my left side is going to approach the asymptote because it's closer to the asymptote. My other side, my right side, is going to connect the dots, and keep going. So that's where I kind of remember the shape of the graph. I can do my domain. Domain is all real numbers. And my range is still related to the asymptote, but this time my y values are all below. My graph is below the asymptote, so its y is less than 0. A couple more of these. I would probably, if I were you, pause the video, see if you can do these by yourself, but I'll keep going. If I make a table x and y, I plug in 0, 1, and 2, I get 2/3 times 2 to the 0, which is just 2/3 or 0.67, or if you even want to round to the 10th, 0.7. Then 1 is 2/3 times 2 to the 1st, which is 4/3 or 1.3. And then I do 2/3 times 2 to the 2nd, which is 2.7. So I can graph these points. I've got 0, 0.7, 1, 1.3, 2, 2.7. My horizontal asymptote is going to be y equals 0. So graph that. And then I want one of my sides of my graph to approach the asymptote, the other side to go away. So this side will approach, the other side I kind of connect the dots and keep going. Domain is all real numbers. Range is y greater than 0. Here I've got x, y, plug in 0, 1, and 2. When I plug in 0, I get -2 times 2 to the 0 is -2. When I plug in 1, I get -2 times 2 to the 1 is -4. And then -2 times 2 to the 2 is -8. So 0, -2, 1, -4, and 2, -8. Zero, -2, 1, -4, and 2, -8. I can draw my asymptote, which is y equals 0. And then I've got to think which side goes to the asymptote, which goes away. So I go with the closer side. The left side will approach the asymptote. Make sure it gets close to the asymptote. And then connect your dots and keep going. Your horizontal asymptote is y equals 0. Domain is all reals, or all real numbers. And your range is related to your asymptote, but this time again, your graph is below the asymptote. So since it's below, we're going to say that it's less than 0. So those are kind of your simple graphs, and all I have to do is plug in 0, 1, and 2. But we know that numbers can shift around where our graphs are. We saw that with parabolas, we saw that with lines, and we saw that with absolute value functions. Which means if we're going to graph any exponential function with y equals a times b x minus h plus k, we're going to have more numbers. We're going to have numbers in the exponent. We're going to have numbers tacked on at the end. We're going to have this h value is going to be our horizontal shift, and then we've got our k value, which will be our vertical shift. We've seen this before as well. Things to notice is that our x minus h, it is a minus, so remember that that is going to go the opposite direction of what we think. So if it's positive, we'll go left. If it's negative, we'll go right. And then our k is a plus, so that is going to be the same direction as our intuition. So what's going to happen is we're going to sketch the original function, the simple one that we've already done, and then we're going to shift it h and k. So I'll show you what that looks like. Number 5, graph each function. I've got y equals 3 times 2 to the x minus 1 minus 4. So these are our shifts, okay? We're going to deal with those later. The first thing that we're going to do is sketch. So please write down sketch y equals 3 times 2 to the x. That's the simple function to plug in. We've already done this 4 times. Plug in 0, 1, and 2. When you plug in 0, you get 3 times 2 to the 0, which is 3. Plug in 1, 3 times 2 to the 1 is 6. Plug in 2, 3 times 2 squared is 12. So I graph 0, 3, 1, 6. 2, 12 is way off the graph, but we can still graph it. And then I draw my asymptote. Okay, one side goes toward the asymptote. Make sure it goes all the way down close to the asymptote. The other side goes away. And that is my just sketch. So I'm going to actually label this as sketch. And then what I need to do is I need to shift using these values. So I'll zoom in here. This minus 1, remember that the minus is the opposite direction. So this is actually, I want to move everything to the right 1. And then our minus 4, this is the same direction as we think, so down 4. That means everything on our graph has to go to the right 1 and down 4. So let's do that. Right 1 and then down 1, 2, 3, 4. And even though I went through the asymptote, that's okay because the asymptote is going to move too. So move right 1 and down 1, 2, 3, 4. And move to the right 1 and down 4 for your 12 as well. That's more of just a approximate because we don't have as much graph space, but that's okay. And then think about the asymptote. I will go another color. If I move the asymptote to the right 1, it doesn't really do anything, but moving it down 4 does. So I'll go 1, 2, 3, 4, and draw my new asymptote right down here. My final graph should have the same shape as the original, so one side is going to go toward the asymptote. The other side will connect the dots and keep going. But this is my final graph. Okay, that's the final product. So that's kind of going to be how you will graph if you have shifts. You'll graph the original, the simple version, and then you will graph those shifts. If you think you can do number 6 without my help, please pause the video and try it. But I will try this one with you as well. The first thing that we'll do is we'll sketch. We want to sketch the simple one. So y equals 2 times 3 to the x. We'll deal with those shifts later. X and y, I plug in 0, 1, and 2. Plug in 0, I get 2 times 3 to the 0 is 2. 2 times 3 to the first is 6. 2 times 3 squared is 18. Double check those. So graph 0, 2, 1, 6. And this one's even more off the graph. And I can graph one side toward the asymptote, one side away from the asymptote. Then I look at these shifts. I have x minus 2. That's going to be to the right 2. That's because that negative 2 is in the opposite direction, and that plus 1 is our up 1. So I'm going to take everything and go right to up 1, right to up 1, and even though this is off the graph, I can still estimate right to up 1. Our asymptote moving to the right 2 doesn't really matter, but going up 1 does. I could then connect our points going toward the asymptote on one side and going away on the other side. My final graph is this one. Okay. So now let's actually look at the domain and the range and the asymptote for both of these graphs. The first graph, number 5, my domain is always going to be all real numbers. But I really want to concentrate on that horizontal asymptote and the range. So the horizontal asymptote is no longer y equals 0. It's moved down. So I've got y equals negative 4. My range is either going to be all of the values above the asymptote or all of the values below the asymptote. So this time they're all above. So I say y is greater than negative 4. So you can look for this pattern always. Your asymptote is always going to be the dividing line kind of between or for your range. Are we going to be all above that asymptote or all below? We can also see that our asymptote is always going to be related to that number in our equation, that negative 4. So try number 6. Our asymptote this time is y equals 1 because it's moved up 1. Notice that's also this number. Our domain is all reals. And our range, we're again above our asymptote. So we've got y is greater than 1. So those are going to be the things that I expect from you. You need to be able to graph the function using a table and then shifting, and then find your horizontal asymptote, your domain, and your range. This is going to get easier and easier as you practice, so you should really go and do those practice problems. I will see you guys later.